Good afternoon, everyone. Welcome to the 9th lecture. So, in the last lecture we started talking about the greedy algorithm, and this was a new strategy for obtaining a reduced basis method. And the strategy was sort of iterative. In each iteration we scan our parameter space to find for the solution that will produce the largest error, and that's the one that we add on top of our space. So the idea is simple enough. But clearly this really hinges on this error estimator. We need an efficient way of estimating what error we're making at each point in our parameter space. And efficiency in this sense meaning that we don't really want to compute the real solution at every point, because that would be so expensive as a POD equivalent. So most of last lecture was about exactly designing such an error estimator. We saw that there were a couple of approximations that factor in. And this lecture what we're going to do is we're going to reevaluate those approximations, and we're going to see if we can improve that. And the first thing I'll actually do is show you the result of all the approximations that we've made in the previous lecture. So in a sense this is, the objective is twofold. First I want to show you how this would actually be done in practice and what we can improve upon. And secondly it's also meant sort of as a recap of what we've done, because we covered quite a lot of material in the last lecture. One thing I would like to say though is that this stuff is sort of independent of reduced basis methods in a sense. Right? We talked about error estimation, and specifically a posteriori error estimation. And this is a concept that is relevant for in a very general sense in the finite element method. So you'll see these derivations in many classes, also outside of the scope of what we're doing right now. And typically it's considered quite a tricky subject. So I think it's worth spending a little more time on that. Okay, so in order to improve the error estimator, we first kind of need to understand what its current flaws are. So what I've done is I've taken a look at the Matlab project that we're running right now. Yeah, so this should be familiar to you. We have our standard heat equation with some boundary conditions. We have a Dirichlet boundary on the right hand side, and normal boundaries all across the remainder of our domain. And then we had, these were homogeneous, right, the top and the bottom, which means that there is no flux going through that. From a heat perspective, that would be an insulated edge. And then on this side we had some heat influx through our northern boundary condition. And then the parameterization, or the parameters that define this problem, were these different heat coefficients or thermal conductivities in each of the different domains. So we have K1, or kappa 1, kappa 2, and kappa 3. And the objective that you've been working with pretty much throughout all of the lecture, or all of the projects, was that first you create a reduced basis type of strategy, or a reduced sort of model, and after that we're dealing with this design optimization, where we know that our real kappas that we are able to consider in our design have some relation with one another, and we're scanning all possible solutions in the possible design space at that point. And the greedy algorithm, as I just explained, in the reduced basis strategy, what you would do is you add bases that correspond to the points of the highest error. And for that we had designed this error estimator. And the thing that we came up with was that the norm of the error being the norm of the high fidelity finite element solution and the reduced basis solution, so UH minus utility, and so far we've been talking about L2 norms, that was bound by the stability constant of our bilinear form divided by the stability constant of the residual. And then we again had approximation strategies for CB and gamma R that I'll actually talk about in just a second. But this was the strategy that we dealt with. So I would say there was yet another approximation here that we made. And what I want to kind of talk about today is this step. So going from, the true mathematical statement, and I would say that's something that, I would say there's alternative strategies of doing this, but this is kind of fixed. So that's not something we want to improve, but we want to improve our approximation of that error estimator. So let's take actually a look at what the error estimator is doing compared with the real error for this model problem that you should be familiar with at this point. Yeah, so what I've done is I've scanned the parameters kappa that we allow in our design optimization. So I've walked through those and I've computed the real error, so that's relatively expensive, right? I'm just doing this for illustrative purposes. And I've computed the error estimator that we discussed in the last lecture. So I've computed both of the left side and the right side of this equation. What I obtained was this graph. Yeah, so this is the real error. Real. And this was the estimated error. Yeah, and as I said, so what we're doing is we're going from this kappa star, and this kappa star is defining all the different material parameters in each of the different segments of our model problem. So what we're seeing here is that the real error is clearly a lot lower than our estimate. Now in principle that's kind of what we're defining it to be, right? We have that the error is bound by that, so this was, so this is an upper limit. So that's good, because we want to be able to say for sure that whatever error we're making is smaller than that estimate, and well, that's clearly the case. Another nice thing is that it's following the shape actually quite well, right? We see these peaks and these valleys, and even the shapes in between, they look quite similar. Now the clear problem that we're seeing right now is that the estimate itself is still quite a few orders of magnitude away from the real error. Yeah, and that's something that we want to improve upon, and that's what we'll do in this lecture. So a couple of the things that we're actually also seeing from this graph is really how the greedy algorithm works. The greedy algorithm is adding to the reduced basis set different solutions in the parameter space. So what we can actually see is that these points correspond to, well, I would say these are actually zero errors. And that is because the reduced basis method incorporates that point. That's the point that we've added to the reduced basis set during the greedy algorithm. So our reduced basis method is able to 100% accurately compute the solution at that parameter point. So the error should be zero. Yeah, so I think if you would compute this at a finer grid, you would actually find the zero at that point. Or at least machine accuracy, right? Okay, so in order to understand what we can improve upon in our estimate, we first have to go back a little bit and talk about how we designed our a posteriori error estimate. Yeah, so this is really just a very short summary of the complete last lecture. And what we kind of hinged upon was the notion of these two stability statements. The first stability statement was that if I take my bilinear form and I substitute the same function in both slots at some material parameter or some point in our material space, or point in our parameter space, then it is bound from below by some stability constant CB, which we typically call the coercivity constant, which becomes parameter dependent, multiplied by the norm of this function v squared. And last lecture I focused on L2 norms because that's kind of what we're familiar with. Today I want to extend this actually to the more natural setting and change this to an L2 or an H1 norm. Sorry. So I have to. That's exactly what I don't want to do. And today we'll look at this H1 norm. And this is really the more natural setting because we've said that our bilinear form can take functions v in H1. And recall H1 was this infinite dimensional space of functions that we can take a derivative of. That's pretty much very roughly what the definition of that space was. So this was one stability definition that we came up with, and the second one for the linear form, and really in general all kinds of linear forms, is that it's bound from above by this constant g. Oh, sorry, this should still be an L. I'm getting ahead of myself. Which is also parameter dependent, times the norm of v and H1. And this is also true for all v and H1. Yeah, so the way that we should think about that, and just to be clear, a linear form, recall, that's anything that takes a function and gives a number, right? So this could be an integral over a volume, this could be a weighted integral over a volume, it could be an integral over a boundary, it could be a function evaluation at a point, it could be the evaluation of the derivative at a point, right? So everything that takes a function and gives a value falls within this context in the sense of a linear form. And what this statement is sort of saying is the extent to which that whatever we plug in can explode. Yeah? So suppose that we plug in anything that has this norm, so this magnitude of 1, a unit value, so these are normalized functions in that sense, then the question is, how much bigger does my output become after I substitute it into this L? Well, at maximum it would be this gamma L. So it's sort of a measure of how much things grow. It's also called the boundedness coefficient, because it's a measure for how bounded things are once you plug them into this linear form. Okay, so today we're going to talk about this in the H1 norm. So just to help you remember what that was, so we defined the H1 norm of a function. Well, in a general sense, the norm was defined to be the inner product with itself. Yeah, but now we're talking about an H1 inner product, right? Not an L2 inner product. So what was an H1 inner product? Well, an H1 inner product is simply the sum of the L2 inner product plus the L2 inner product of the gradients. Okay, so this is the norm that we'll be using, and this is also the norm in which we're going to measure our errors. Yeah, so the error is going to be measured in an L2 sense, and also in the L2 sense of its gradients. So compared to last lecture we focused on this L2 part, and then we saw that we could actually write this with the mass matrix. Yeah, because if we substitute functions v in that finite dimensional space as sums of coefficients times basis functions, then we saw that that factors out, right? So if we write v with this coefficient matrix or coefficient vector, then we found that that is actually this. Yeah, where the hats are the coefficients of the functions. And in a similar sense, we're actually also familiar with this right lid, and this is namely our stiffness matrix. Yeah? So we can also multiply that with coefficient vectors. And this is an identity, right? As long as v can be written as the sum of coefficients times bases, which we could also write as this line vector multiplied by a standing vector. So we'll actually write this in a simplistic form as a m star because in a sense this is still, in the way that we talk about this is still a mass matrix. This is the mass matrix associated to the H1 inner product, as opposed to the mass matrix that we're more familiar with, which corresponds to an L2 inner product. Okay, so then what did we do? Well, we began with this statement that the bilinear form is equal to the linear form for all test functions for the true solution to the problem. Yeah, so we began with pretty much a trivial statement, b of u, where u is now the solution to the problem, v at the parameter mu. Well, that we know is going to be equal to the linear form v for all functions v in. And I'll already jump to the finite dimensional case, so we've replaced our spaces H1, our sublet spaces, by our finite element spaces. Yeah, but these are still high dimensional, right? These are 10 million degrees of freedom. So this we know to be true. What we're going to do next is we're going to subtract something from this, which by itself only makes a limited amount of sense, but we'll be subtracting it from both sides, so it's going to be the same thing as adding 0. From both sides we'll subtract the reduced basis function solution at that parameter location substituted in the bilinear form. So this is what we're going to subtract. And not only that, after we've subtracted that, we're also going to choose v, which might be, well, this has to be true for all possible v's in our finite element space, so it might also be true for u, or it is also true for u minus utility. Yeah, for that choice of test function, this statement has to be true, because it's true for all test functions. So what do I end up, what statement do I end up with after I've done that? Well, first of all, I have b, u minus utility, right? That's the subtraction here. These are linear forms, so I can do that. After that, I've substituted this expression for v. And we're doing this at our parameter point mu. And that is equal to, well, there's little I can subtract here, so I'll just say L of v minus b u tilde v at mu. And this is what we would define to be the residual. Yeah, so that's the real right-hand side, the L, so that would be the force vector, whatever, minus, well, whatever will be left after I've substituted my reduced basis solution into that high-dimensional stiffness matrix. Yeah? So that would not be 0. It would be 0 for a subset of test functions v, but not for all test functions. And, well, clearly I'm also substituting this here and there. So this is still at u minus u tilde. And it should also be parameter dependent. Now, after I've done that, I'll make use of my stability definitions. I actually flip the orientation of the first ones, because I want to start with this statement, and then I find that CB at mu, that's a stability parameter, times the norm of v squared. Well, right now v is this u minus u tilde, measured now in the h1 norm, right? That is going to be smaller than or equal to, well, this, which is equal to, well, that, which is going to be smaller than or equal to, and then we have the second statement, and specifically applying that to this, the residual. The residual is also a linear form acting on v, so we get gamma, and then I'll use r to indicate this is for the residual, at mu, times the norm of, well, v. What is v? Again, that's u minus u tilde, measured in the h1 norm. So I actually don't care about the things that are in the center, I only care about the leftmost statement and the rightmost one. And if we combine those two, then we find that we can actually cancel this one of the norms with the square, and we get that the norm of u minus u tilde, measured in the h1 sense, will be smaller than or equal to gamma r divided by cb. Yeah, so this is really only in a few minutes a complete summary of what we did in the beginning of the last lecture. And this is to a large extent how we deal with the posteriori error estimates in finite element methods. Now at that point we said, well, we're not quite so happy with this yet. And the reason for that is we want to be able to do this cheaply. And right now we have to compute CB from this eigenvalue problem, which we have to do at every parameter point. And similarly, gamma r also follows from sort of an eigenvalue problem, which we would have to compute at every point, so that's going to be very expensive. And we don't want to do things that are very expensive, because we want to be able to do things at many, many points. So the second half of the lecture was about finding ways of computing gamma r and CB in a cheap way. And what we found is that, so I'm going up my slide now, that an expression that we proposed in last lecture for gamma r is that it is bound from above by the minimum eigenvalue, sorry, the maximum eigenvalue of the matrix RT divided by the minimum eigenvalue of the matrix, the mass matrix. And I'll actually rehearse this once we get to this, but I want to have it here. Now this was another place where we've introduced now again upper limits, right? So every time that we add an upper limit, we're reducing the effectiveness of our estimate. So that's something that we want to improve. Yeah, we don't want to have something that is bound from above by a new statement. I just want to be able to compute gamma r in a cheap way. So that's something we'll look at today. And then secondly, for CB, we had this min theta approach, where what we're really doing is we're computing CB at one point in our parameter space, and after that at every other parameter point we're finding a relation between our new parameter point and that reference point, and we also get a lower bound in this case. So this was in this case a lower bound for our CB at every other parameter point. So these are the two approaches that I want to discuss today and we can improve upon. Now first, to kind of illustrate to you why these are actually part of the problem. So again, here we have our estimated error versus real error. And our estimate consists of this gamma R and this CB. And this is our gamma R approximation. So this is with that gamma R as an upper limit of the maximum divided by the minimum eigenvalue of the mass and the eigenvalue of this RRT matrix. And this is the real gamma R. Yeah, so we see that by making our approximation for gamma R, which is actually the norm of the residual, that's what that is called, we introduce an error that is, or what is this? This is, well, this is close to a factor of 10, right? Yeah. So that approximation is already introducing an order of magnitude mismatch between our estimate and the real error. So that's something that we want to improve upon. How about this CB? Well, our CB approximation using this min theta approach, it looks like this. This is the real CB. And this is the estimated CB. So here we also see that at the extreme cases, we are about a factor of 5 off. Yeah, and here we actually already see also how this min theta approach works. We're taking this reference point, and at every new point in our domain, we're sort of taking the min theta approach is then with respect to that reference point. So indeed we see that at the reference point, well, that's exactly where we would get the real CB. Okay, so these are the two parts of the story that still have flaws in them and that we want to improve upon. And I'll actually start with this CB approximation. Okay. So, what was our strategy for obtaining the CB again? Well, first of all, we said that if we take our bilinear form and we substitute, well, let me first write down the definition again of CB so that we're clear on that. So, V at some parameter nu is going to be larger than or equal to the stability constant B, which becomes parameter dependent, times the norm of V, which 1 square, and that has to be true for all possible functions that we can substitute in our bilinear form. And I'll focus on the finite element truth problem case, so the high dimensional finite element space. Well, the way that we obtained our min theta approach, or what we did for our min theta approach, was to say, well, we know that we have this affine decomposition of our bilinear form, so that it becomes this sum over bilinear forms that are independent of the parameter, and we have capital Q B of those, and then multiplied by these theta functions. And these theta functions are then parameter dependent, and what the min theta approach was we're going to actually substitute right here our reference point, and then we're going to factor out up front the minimum of, well, the division by that guy again, because that guy is incorrect, right? We should be evaluating it at a mu, not a mu star. So we're going to divide that out again. And multiply by what was actually correct. And then we can see that if we factor out the minimum of those guys, then this becomes a lower bound. And for this guy, we saw, well, this is exactly B at V reference location. So using that, we can actually find that the true stability coefficient at any parameter mu has as a lower bound this min theta strategy multiplied by the CB at this reference location. And again, that's why we see this overlap at that one point, which is the reference location, because at that point, well, the ratio between these thetas is 1 everywhere for each of the thetas, so that's simply 1 times the CB. Yeah? So we retain that value at the reference location. Well, there's really nothing that kind of makes us do this specifically for one point. What we could do is get multiple reference locations throughout our parameter grid. Not one, maybe one and then a bunch of them on the corners as well. And since we know that for each of those reference locations, our real CB is going to be larger than well, any one of those, we can take the maximum of those guys and use that as our new approximation. So what am I saying here? Well, I'm proposing that instead of doing this only for mu star, I'm actually going to also do this for a new reference point. So I know that CB mu is also larger than the same statement for some other reference point. So I'll call this reference point number 2 times the CB at the reference point number 2. And similarly, I can do this also for reference point number 3. Multiply by CB at mu reference point number 3. Right? And I can keep on doing this for m reference points. And since my true CB will be larger than any one of those, what I can simply do is I can take the maximum of these, and that will be my tightest bound. Yeah? So each one of those will be a lower bound, and then I'll take the maximum to get the tightest lower bound. Yeah? So then I'll actually define my CB, my new lower estimate, as the maximum over all of these m reference points. So I is equal to 1 to n times, well, let me write it out one more time explicitly, times the minimum of theta b q. This is now a minimum of all the q's at mu divided by theta b q at mu star reference point number I times CB at mu star reference point I. Yeah, so I'm going to take the largest one of my lower bounds. And well, the name that we have for this quite clearly is the multi-parameter min theta approach. Okay, so how well does that work? Well, I can actually show you. So this was again with the one parameter, so that's why this was already sort of in the legend here. So this is a one parameter min theta approximation. And if I now add a bunch of these reference locations, right, mu star 2, and also on the edge, we get mu star number 3, and maybe another one over here. And typically it's good to consider the corners, right, those are the extreme cases. Then we find something that looks like this. So this is the multi-parameter min theta approximation, yeah, where again we have our original reference and each of the other references. And as expected, we find that at each of the reference points, if we reconsider those, then we will get, well, exactly the CB at that location. I'm a bit surprised that my X range goes so high. I thought this should be capacitor. I'm not sure what I'm doing there. Okay, yeah, so we see what we expect to see. We get a lower estimate, yeah, so this pink line is still a lower estimate of the red line. It's at each point it is less than or equal to the red line. And at those chosen multi-parameter reference locations, we get the exact CB as expected. Okay, so that's already a step forward, right? We're moving from an error of, well, in this extreme case, an error that's a factor 5 to an error that's a factor 0. But in a less extreme case, we're improving by a factor of roughly 2, right? So that's something, that's already something. But we saw that the major part of where we're making a mistake was still in the norm of the residual. Yeah? So if I go back a few steps, this is where I really saw that the approximation of our gamma r is just completely flawed with respect to the real gamma r. Yeah? So that's really where we can hope to gain some improvement. Okay, so let me call this part 1. And then we'll start with the improvement number 2. Okay, let me write down again what our definition was. What do we actually want to compute? Well, we had that the residual, which is a linear form, so it takes the function v and it spits out a scalar value, but it's also parameter dependent. That is bound from above by this stability parameter gamma r, which also becomes parameter dependent, multiplied by the norm v in H1. And again, this has to hold true for all functions v in, well, right now, our high dimensional finite element space. Now, this was a little tricky to work with. We're trying to couple these to eigenvalues, and we could do that before because the equivalence of a bilinear form was a matrix, and then we have sort of a, well, then we have the notion of an eigenvalue. We don't really have a bilinear form. We don't have a bilinear form. We have a linear form, so we kind of have to do this a little differently. And we're going to do this. First, we're going to write this in this vector notation just to make sure that we have an idea of where we're going. Right? So we write v as, again, this vector of coefficient transpose times this vector of basis functions. And that's always substitute in this norm and also in the residual, which in principle just takes functions and spits out numbers. But if we substitute that definition of v, then we can rewrite this whole statement as v hat transpose times now a residual vector. And this would now become parameter dependent as well. Yeah, so the statement above that was a linear form, would be an integral, whatever. And in this finite dimensional case, we can write that as this or the vector of coefficients multiplied by now this data vector. Now that's going to be smaller than or equal to gamma r times mu. And I also want to emphasize this is not an approximation, right? This is due to our definitions of all our v's. Every v in our finite element space can be written exactly like that, which means that every residual operator acting on any function v can also be written like this vector-vector multiplication. There's no approximation there. The approximation was already before, where we've changed the Sobolev space H1 into UH. So what do we get from here? Well, we can go up a little bit, and we saw that, oh, I put that in the slides actually. And we saw that here the norm in H1 of any vector v squared is equal to, well, this multiplication of v m star v. So right now I don't have to square those, so I'll have to square root this, but still I would get v transpose m star v. Now actually to note, I'll be clear in my differences, so r is a vector but m is a matrix, right? And again there has to be a square root here. Now I don't like square roots, so what I'm going to do is I'm going to square both sides. Since, well, both sides are simply scalar values, right? I can do that. And so since, because, well, this is also just a scalar value, so I can also take the transpose of the scalar value. So what this will end up being is I'll have v hat t times r, that's what I had. now multiplied by itself, transposed, so I get R T V hat. And that's going to be smaller than or equal to gamma R mu square times V hat T M star V. Okay, so that's something that I can start working with. What we have right now is this is a matrix. Well, and actually I can just write down the dimensions. So the dimensions of this matrix are big N times big N, right? Where big N was the dimensionality of our high fidelity finite element approximation. Same thing for this Miles matrix, N times big N. And each of the vectors are simply either 1 by N or N by 1. And last time we looked at equations like this, and we saw that the stability values that we're looking for, they're actually solutions to the eigenvalue problem that this corresponds to, and that eigenvalue problem, this generalized eigenvalue problem, then looks like this: R transpose V hat, well, is equal to, it's an eigenvalue problem, is equal to lambda I times M star V hat. And so gamma R mu square is the maximum eigenvalue of that. I'll give this a number. Yeah? So if we could obtain the eigenvalues of this eigenvalue problem, well, then I would know my gamma R. And in a sense, that is actually exactly how I computed this red line, right? That's the eigenvalues of that eigenvalue problem. But this is a very expensive eigenvalue problem, and I can do that just to show you guys this graph, but in principle I wouldn't want to do this during my reduced basis method. So we're going to still have to manipulate this a little bit. And the first thing we can do is, well, we can always write a generalized eigenvalue problem as a regular eigenvalue problem. Well, not always, but if the right-hand side of the Maas matrix is invertible. And in this case, well, because it is a Maas matrix, it is invertible. And what that gives me is M star inverse R RT yeah, so this is now a regular eigenvalue problem, where this guy was n by n. This is n by 1, this is 1 by n, this is n by 1, and this is also n by 1. Yeah, so I've changed this generalized eigenvalue problem to a normal eigenvalue problem, and this is also how we obtained our upper limit for gamma R, right? If you remember, we said here gamma R in the top left corner of this slide, we said that it's the ratio of the maximum eigenvalue of RRT divided by the minimal eigenvalue of M. Well, you can now see that that's where this is coming from, right? We have the maximum eigenvalue of RT, and well, this is M inverse, right? Sort of a division, so that would be divided by then the minimum eigenvalue of this M, and that would be an upper limit of the maximum eigenvalue of this problem. So actually, so yes, this should still have been a square root. Yeah. Okay, but I really haven't solved anything yet. This is still way too expensive, and I don't want to execute this computation. So I have to think about this a little bit more. And there's a couple of things to note from this equation. The thing I want to emphasize on here is that the rank of each of the matrices that we're working with here. So M is a Maas matrix. It corresponds to an inner product, right? It's H1 inner product. There's all kinds of properties associated with something like that. We know it's symmetric. But we also know that it is positive definite. Positive definite means that all its eigenvalues are positive. Well, the least thing that means is that it has a complete set of eigenvalues. What that means is that it's full rank. That's kind of the conclusion that I want to draw here. So M is full rank. And what full rank meant is that each of its rows, and because it's square, also each of its columns, are linearly independent of each other. And this meant that, well, if you have n rows, then because they're linearly independent, we span the complete space of Rn. This is different for the second matrix that we're dealing with here, this RRT. This is composed out of one vector multiplied by one other vector. Yeah, so each of the rows of that matrix is linearly dependent with each of the other rows of that matrix. Same for each of the columns, because, well, that's how we construct it. We construct those columns multiplied by the rows. Yeah, so each column is just a new multiplicative relation with each of the other columns. So that guy, so this one was full rank, but this guy only has rank 1. And I'm multiplying these by each other. Now what happens if you multiply a full rank matrix with a lower rank matrix? Well, the lower rank matrix is going to spoil the result, right? So the full rank matrix has all the information that the matrix can house, whereas the low rank matrix only has a limited amount of information. And if you multiply those by each other, the result will always still be a rank 1 matrix. Yeah? So you're kind of throwing out all kinds of additional information that the mass matrix in this case is housing. So M star inverse multiplied by RRT is a rank 1 matrix. Now why is that interesting? A rank 1 matrix means that there is one non-zero eigenvalue. Eigenvalue, eigenvector couple. So what I can do is I can look at this equation, play around a little bit, and once I find a single vector v, that if I substitute that into this equation star star, that behaves, well, like this statement is saying, like an eigenvalue, then I immediately know that is the only eigenvalue that this one has, and I immediately know that this is also then the maximum eigenvalue that this guy has. And it turns out that there's actually a pretty obvious choice here, and that is if I choose v hat, my vector of coefficients, to be equal to, I want to say mass star minus 1 times r. Let me check that. Yeah. Yeah. So if I make this choice, and I had reasons for making this choice, but I'll just show you that this is actually the one that satisfies number 2. So we substitute then what this equation is going to say is m star inverse times RT. Oh, and that's exactly what I wanted to substitute. So we have m star inverse r. So what do these matrices multiplications look like? We have n times n, then we have n times 1, and 1 times n, and n times n, and n times 1. So if we look at this multiplication, I can do them in principle in every order, right? So what I see here, this is sort of a breakpoint, because we start with 1 and we end with 1. So if I would first multiply all these things through, this will be a scalar. And what we have on the left side then is n times n multiplied by n times 1. So this gives an n times 1 vector. So what is this? Well, this is going to give me m star minus 1 times r, right? That's the vector. Multiplied by the scalar, which is the value RT, m star inverse r. Well, this guy was exactly v hat. So what I'm seeing that if I substitute this choice that I made of v hat into this leftmost position, then the output will be v hat multiplied by a scalar, which will then automatically be my Lagrange multiplier, or my eigenvalue. Lambda is also the symbol for Lagrange multiplier. Moreover, what I know is because m was full rank, also m inverse is positive definite, or sorry, because m was positive definite, also m inverse is positive definite, and well, this is then also a normed quantity, so this guy is actually larger than 0. Yeah, so not only do I know that that is precisely the one eigenvalue that this system allows or houses, it is also positive, and it will thus automatically be the maximum eigenvalue. Okay, so what do I know now? I know now that the gamma r, the one I'm looking for, which again is mu dependent, that is equal to the square root of RT n star inverse times r square root. And I know this without having to compute any kinds of eigenvalue problems, because that's what I just did by hand, right? I worked this out. Now, is this now helping us? So the r vectors, those we can compute relatively cheaply, but m inverse not so much. Now you might say you would only have to do this once, but that's going to be a dense matrix, so you would have to multiply huge dense matrices by these residual vectors, so that's also kind of not what we want to do. So I'm not quite done yet, but I'm getting somewhere. So now we're looking for a strategy of making this cheap. And recall, what we want to do is for every parameter point that we want to consider for the error estimate, we can compute r, and we want to then, after that, so we can compute the residual vector, and from that we want to compute gamma r. So what exactly was this coefficient or vector of coefficients for r? Again, what was this? What was the definition of that? Well, I've been kind of dropping its parameter dependence already from the start, but of course there should be a parameter dependence in here, right? So what was this vector? Well, we had r, and I'll reintroduce its parameter dependence just for clarification. Remember, that was the linear form minus the bilinear form where we have substituted our reduced basis solution in the first slot. Well, linear form also had a vector associated to that, that was f. A bilinear form had our stiffness matrix associated to that, which at this point becomes mu dependent, and actually this one also. And we have multiplied this by our reduced basis solution. Yeah, so if I were to have multiplied this by the true solution, then this will be 0, right? For the true solution, f is equal to k times u. But because we're using reduced basis method, k times utility is not equal to f, and exactly the difference is the residual. Which, just to be clear, is something else in the error, right? But it is a measure of the error, according to the error estimate that we just proposed. Okay, and I can write this in one alternative way still, so f, and I'll drop the parameter dependence again, but I still want to, again, make that clear to everyone. Each vector and matrix is still parameter dependent. So we had k, and the solution vector utility, we could write that as that vector v times our solution w, where, let's clarify this again, we have n times 1, then we have n times 1, we have n times n, and this guy has small n times 1, right? So if we have a reduced basis method with 5 bases, then small n is 5, and this was the connection between them. So big N times small n. Yeah, okay. Okay, so I've introduced this V in a couple of the slides, so I hope this is clear. Yeah, so this is how you would get the relation between the vector of coefficients associated to each of the bases and the utility. So the vector of coefficients associated to the high fidelity basis. So now let's try to compute gamma r, and actually I'll compute gamma r squared because I don't want to deal with the square root for now, but obviously you can just square root the end. Yeah, so what I want to compute is RT times m. Yeah, I'll just write also, yeah, I want to simplify my notation at this point, so I'm just going to use m. Be clear that this should actually be m star, because again, a mass matrix has always an inner product associated with it, and the standard choice L2 is just that, a standard choice, right? So, but right now in our mass matrix, we're using the H1 inner product, potato potato. Okay, RT MR, that's what we're going to compute, and after we take the square root. And this was our definition of R. So I can just substitute that, right? So I'm taking F minus K V W utility transpose. Now I'll already plug in that mass matrix, just for clarification. You get M times F minus M times K times V W. Oh, I can work out the brackets here. So again, there's no approximations here, right? So everything up until now, we're doing the exact definition of gamma r. So we have F transpose MF F times that guy, so minus F transpose mass K minus this transpose multiplied by that, so it's going to give us W transpose times V transpose times K transpose times MF plus, again this guy transpose W utility T times M K V W. Okay, now it doesn't look like this is really helping us quite so much. But the nice thing about this expression is that all our reduced basis stuff is kind of factored out. It's here, it's here, it's here, and it's here. And actually the second and the third term, they're the same, so you can just multiply by 2 and take one of them. So why does that help? Well, remember again, we have this affine decomposition of each of our force vectors and each of our stiffness matrices. So remember, we would write our force vector at some parameter point mu as the sum over Q. Well, I used L before, right? Because these are the linear forms, even though we're writing this now in a vector sense, of theta L Q times parameter independent force vectors. And also our stiffness matrices, which in principle are all parameter dependent, becomes the sum over bilinear form parts of theta B, bilinear form, Q mu K. So independent stiffness matrices. So I'm not going to work this out after this because it just becomes a huge array of multiplications, but I do want to illustrate what's going to happen. You would substitute these expressions in each of the different parts of this sum. Yeah, so this is simply, by the way, just to clarify, it's 2 times one of these, right? So this is the same. So you'd work out the sum, you would write that, and you would find that you can actually write that as a collection of parameter independent components. So if we do that, then the first term, Ft Mf, well this guy only depends, well the mass matrix is constant, right? So this only depends on this parameter dependent F, mu, So this, how many different components, parameter independent components is this going to give? Well, it's going to give QL here multiplied by QL. Yeah? So actually I'm just multiplying each of these FQs with the mass matrix and then again with one of these FQs. And actually a couple of them might be dependent, so it might actually be lower than this. But what am I actually computing? For each of the parts in the series expansion, I'm just getting a scalar value. Yeah, so I'm getting QL times QL scalar values. And each of the scalar values is still dependent on this theta, but for a new parameter point, I can simply compute the thetas and multiply those by these pre-computed expressions which were just scalar values. So at that point, after I've pre-computed that, it becomes extremely, extremely cheap. Same thing happens for these two other terms. Yeah, I have 2 times, it doesn't really matter which one I use, F, T, M, K, G, yeah. So how many of these am I getting? Well, I'm getting QL, different components from my force vector in this affine decomposition. And I'm getting QB, stiffness contributions. So I'm getting QL times QB times a vector with small n components. Now, remember if we work out the matrix multiplication, I have 1 times big N times big N, big N times big N, big N times small n. Yeah? So I'm getting QL times QB of these small n sized vectors. Again, that's no problem in terms of storage, all small data. And lastly, I get V transpose K M K V. Again, just to be clear, this is parameter dependent, this is parameter dependent. So how many components am I getting from that in my pre-computation? Well, again, I have my bilinear form, my K is dependent on QB bilinear forms, and I'm multiplying that by M, and then I'm multiplying it by K again, and if everything is symmetric it becomes even less than this, but you would again have QB times QB, N times N matrices. Yeah, because this one was N times big N, big N, big N, big N, big N, big N times small n. So again, this is also very cheap to store. And once I have pre-computed all these components, then, given a reduced basis setup, I can automatically, at my new parameter point, compute, well, first my W tilde, my vector of coefficients for the reduced basis methods. After that, carry out, well, this sum, which becomes my gamma r square. And I can do that sum very, very cheaply because I've pre-computed all these expensive computations. And I see that I made a big mistake somewhere. Significantly simplified the whole problem. There should be a -1 for each of the mass parts. But that does not change the story that I'm telling here. Yeah? Although it kind of emphasizes why you want to do this a priori. You want to do this in the offline stage, where you have the computational expense at your available to you, because then you can do all these inverse matrix multiplications. And also in terms of error estimation, if you want to do that cheap, also during the offline stage, you would also pre-compute this. Yeah, so with this complete decomposition where you've pre-computed as much as possible during an offline phase, you have cheap error evaluation in the offline phase during the greedy basis generation. So one of the things this means is that you're able to scan more points in your parameter space, right? If you have a very expensive error estimator, well, what it comes down to is that you simply cannot sample as many points as you would with a cheap error estimator. So that's one aspect, and the second aspect that's actually very important as well is that we have cheap error evaluation in the online phase. And that's actually something that we haven't really talked about. So far, we've all, in a greedy algorithm, we focused on this error estimator exclusively during the offline phase for your greedy algorithm. And that meant that at the time you will be able to make the claim that my complete reduced basis method is able to handle this parameterized problem with a maximum error of, and then you would have an error tolerance. But on top of that, what we can do right now as well, because we've pre-computed everything, during an online phase, after you've computed your solution of your reduced basis method at a new parameter point, you can cheaply evaluate what the error is without having to compute the truth solution at that point, and also be able to claim, well, my error is at maximum going to be equal to that. Yeah, so that's an incredibly powerful capability without having to do any expensive computations. So with everything extremely cheaply computable, you'll be able to get a solution and you'll be able to say at maximum my error is going to have a value of, well, x. So this is actually this is called certification. Of reduced basis methods. And you can imagine that that's actually quite important because it's quite easy to mess this up, right? It's quite easy to generate some arbitrary reduced basis method with a completely undersampled POD strategy or whatever. And then you would be able to use that to tackle an expensive parameter optimization strategy. But you would have no way of saying if this is a good solution or not, right? So and this is precisely what's giving you that capability. The capability of during an online phase being able to say, well, my solution is good, is correct. Or at least has a maximum error of this error threshold, error tolerance. Okay, so suppose that we've done all that, and I've implemented all of that. What can we gain? Yeah, remember this was the estimated versus the real in our naive estimation strategy from last week, and now we've improved this gamma R computation. Actually, we compute now the exact gamma R, and we're able to do that very, very cheaply. And we've improved the computation of CB using this multi-parameter min theta approach. Yeah, so this was the original gamma R approximation, and this is the one that we can compute now. So we improve our error estimate by a factor of 10. Then this was our original CB approximation using the min theta approach. Now we use this multi-parameter min theta approach. Yeah, so we reduce our error by the error of our error estimator by another factor of 2. Which means that in the end we get a graph like this. Yeah, so again, this was our original estimator. Yeah, so I'm calling this also a crude error estimator. This is the real error. And this is now the improved version. So we still see all the same positive properties. We still see that it drops to 0 at the points where we construct our greedy bases, right? That's what we expect, because at those points we will be able to capture the exact solution up until, well, the numerical error tolerance. And so we see that at the center and each of the corners. We also see that it follows the same curvature. And compared to the original estimate, we've reduced by, well, homogeneously by a factor of an order of magnitude, maybe slightly more. Still though, we see that we have an error with respect to the real error estimate, the actual real error of 2 orders of magnitude, like a factor of 100 is what I'm seeing. The difference between those guys is... So I'm actually a little bit surprised by this. I'm not sure why this is. I'm not an expert in posterior error estimates, but what I know roughly is that we should be anticipating a factor, an error estimator efficiency of 5 to 10, right? And we're seeing 100. So 5 to 10, maybe 20, but 100 is clearly too much. So I'm actually not sure why this is. This is something I'll still look into. I kind of don't think I made a mistake at this point, although I might have. So I don't know if you care to challenge me and see if you do this, you get some other results, then I'd be happy to have a look. But still, what we're seeing is we've improved this by a factor of 10, and I think that in more realistic cases, you would get closer to this factor 5-10 efficiency that we usually see. Okay, so then to wrap this kind of up, I've shown this slide a couple of times, and each time I show this, I kind of add a component, and the component that I added this time is this error estimation part, all the way in the bottom. Yeah, and this is also kind of independent of whether we use a greedy method or a POD method. In principle, you would want to do this. You would want to, in your offline phase, compute all the necessary components, so the min theta or multi-parameter min theta approximation to the CBs, and the computation of all these different components here to compute the residual norm. And once you've done that, you'll be able to, during the online phase, right, the red boxes here, you'll be able to compute, after you've computed your reduced basis approximation at the new parameter point, you'll be able to compute the error limit that you're making at that point. And that's what's making a reduced basis method from some arbitrary approximation problem which might be good, might not be good, into something that is certified and for which you can guarantee that your solution is going to be accurate. Right? That's what this certification is about. So that's what I had in mind for today. I think we're a little shorter than usual. I would say that's fine. We largely kind of summarized the workflow of the greedy algorithm when we refined the important aspects. So to kind of wrap this up and make a connection with what we'll still do in the future. So the deadline for the greedy project is, as usual, next week. Although I think I made a typo that you're lucky with in the deadline date. So I think I set the date on Thursday, so we'll stick with that. You can hand it in on Thursday, it's no problem. So still on Tuesday will be the last project session, so please attend, ask any questions that are bugging you. So what we'll do after that, as I've said a couple of times, is we're going to do these individual projects, and I'll actually introduce those in the live lecture on next week, Thursday. Yeah, so I think right now there are still 6 people that are actively participating. They're handing in the homeworks. So I've written 6, or I'm working on writing 6 of these individual project descriptions. And what I'll do next week is I'll pitch those. So each one is like a page with some story. A couple of research questions that I would be interested in if you could I don't know, work on that and see what you can find out in these directions. Yeah, so these are really sort of open questions, right? There's no true answer to any of the things that I'm asking, and this is up to you to figure out what you can figure out. So I'll pitch those problems. They will vary in difficulty. Now, if you pick a more difficult problem, then I of course take that into account, right? And if you use one of the easier problems, then I'll also take that into account and have higher expectations. Although none of them is going to be easy and none of them is going to be impossibly difficult. So what I'll do next week is I'll pitch those, I'll go over those, and because there will be as many as there are students, that means that we're going to have to distribute those one-to-one. And I will simply use a first come, first serve basis. Yeah? So after the lecture, you can email me with your top 3, so I'll rehearse this also next week, but you can email me with your top 3 of projects that you're interested in, and I will actually just, the first person that asks for any particular problem as the top 1 will get that one, and then I'll scratch it off the list, perpetuating until we've distributed our projects. Yeah, so I think then we'll see who is actually watching the live lectures and who is not. So that's everything I had in mind for today. So thank you for your attendance, and then I'll see you either next week Tuesday or next week Thursday.